Okay, so for the exercises, I'll try to. So I think realistically, if I want to cover what I want to cover today, I won't. I don't think I'll have a chance to actually discuss the exercises. But what I'll try to do is write out the solutions and also publish it on the school website. Um, so in the last lecture, so well up to now, we introduced the kind of maybe the textbook Maxwell block equations. We really saw that within these equations, anything simple that you try to do, quantum memory or photon gate, just kind of fails horribly with realistic parameters. And then yesterday we discussed that maybe one way forward is to use multiple scattering of light and wave interference. And then we studied a few kind of like classical type phenomena that 1D chain acts as a waveguide for single photons, a 2D array acts as a mirror, and then we showed that you could actually kind of take these classical effects and then somehow functionalize them into a quantum memory that all of a sudden gives you an exponentially better error bounds. And then by adding Rydberg interactions into a 2D array, I also showed how you can create a photon-photon quantum gate with kind of a 1% level error rate with realistic resources. So up to now, the consequences of this spin model, we see that they can be quite important, but a lot of the intuition you can really just kind of get from classical optics. So then it turns out that kind of when you go beyond one excitation and two, at some point you really do have to face the fact that you're dealing with this kind of open quantum system, this dissipative spin model. And then, in that case, your classical intuition starts to break down. It's a much bigger and challenging and also exciting frontier. And then today, I hope to at least give you a little bit of a flavor of that. So I'll try to discuss two specific problems or examples. One is what I call a strongly interacting optical lattice clock. And then the second question I want to explore is, if we look at even beyond quantum optics and atoms, but just real materials, why is it that the refractive index of real materials always seems to be so small? So let me, for those of you who are not familiar, let me actually explain what an optical lattice clock is. So these are systems that people are building in the lab today. They're arguably already, maybe the best frequency standard that we have right now. So before we talk about an optical lattice, just talk about a single atom clock. So a clock is just some, frequency standard. So you want this clock to be very robust. You want it to, basically click or divide time very accurately. And it turns out that the best way we know how to do that is just to use atoms. So the idea is the following: even if I take a single atom, if I take strontium, for example, the nice thing of strontium is any two strontium atoms are the same. So I build a strontium clock, you build a strontium clock. In principle, they should tick in exactly the same way. That's what makes it a nice. That's what makes atoms a nice frequency standard. And then, kind of to lowest order, ideally, if you want a good clock, it should have a very large transition frequency, right? Because then you can kind of divide time into finer and finer units. And so, typically you would want to take an atom with an optical transition, just like we've been talking about the whole time. And also, you would like maybe the single atom, if it's up in the excited state, to actually live a very long time. And so there are kind of exotic atomic transitions where, for example, you bring the atom up to the excited state, and even if it's just a single atom, that excited state might take on the order of minutes to decay down into the ground state. Okay, so this is just it has a well-defined frequency, which is hopefully independent of which, again, like, I have a strontium atom, you have a strontium atom, hopefully they're exactly the same. And it has a very high quality factor because the decay time is very long. And that basically is the kind of key ingredients that you need to create a very good clock or frequency standard. So you could just take one atom, and some people do that. But then you can get greedy and then try to put many atoms together, and then just kind of benefit from signal to noise ratio. So ideally, or the simple story is if I have 1 million atoms in an optical lattice, then I have 1 million independent clocks. So when I average the signal from all those things, I get a signal to noise ratio that's the square root of a million, or 1,000 times better than that of a single clock. So that's the kind of motivation behind using things like strontium atoms in optical lattices. So the kind of often stated goal in this field is to get a fractional frequency uncertainty. So the point is to be able to kind of tell time with a fractional uncertainty relative to the atomic frequency of 10 to the minus 18 in 1 second of your experimental runtime. And so you can ask, what can I do if I have a clock that's accurate to 1 part in 10 to the 18? Well, you can potentially measure things like relativistic effects in real time. So I tried to do a back of the envelope estimate. And I think if you could somehow wear this clock on your wrist as you walk up the stairs, you could tell actually that you're experiencing general relativity. Okay. So that seems pretty cool. The problem, well, an obvious problem is that if you want a clock that's accurate to 1 part in 10 to the 18, you have to understand very well anything that can screw up your clock. And at the level of 1 part in 10 to the 18, there's a million things that can screw up your clock. So some of them are what you call maybe kind of single body effects. So these are effects that you would have even for one isolated atom. So one problem, for example, is that if you have an atom, you have to trap it. The laser light itself could shift the atomic transition frequency, so you have to be able to control that very well. So these are called light shifts. Even if you don't have a trapping laser, you still have black body radiation coming in and weakly interacting with the atom. So the interaction is very weak, but again, at 1 part in 10 to the 18, they can matter. So these are not kind of necessarily easy things to calculate, but you can imagine that the calculation is at least somewhat controlled. On the other hand, though, you can actually have interaction effects, so effects coming from two atoms at close distances. And one thing that can happen is exactly the types of interactions that you get in this kind of spin model that I introduced. The reason for that is if you want a clock, so you're trying to use an optical transition as your clock, you inevitably have to excite atoms up to the excited state. So now you have some atoms up to the excited state, some in the ground state. They'll then therefore interact with exactly these same types of Green's function or dipole-dipole interactions that I introduced before. And remember that these dipole-dipole interactions can become quite strong once the atoms are relatively close together, so within a wavelength of one another. But that's exactly what an optical lattice is. It has, on average, one atom every lambda over 2. And so it kind of raises an interesting question. Your original goal was just to have 1 million independent clocks, but how do you know that these dipole-dipole interactions don't turn your clock into a strongly interacting system? So for example, you have one atom excited, one other in the ground state, and then they start to exchange interactions. You might have collective emission, so the fact that you have many atoms means that the atoms could emit slower or faster than independent atoms. And then it's really kind of open question, do these types of interactions somehow skew your clock or give you an apparent frequency standard or apparent definition of a second that changes depending on strange details of your system? So it's a very hard problem because you're trying to really solve the spin model in the many-body limit. There have been some historical attempts before. You can try mean field. You can try exact diagonalization on very small systems. You can look at early times before correlations really start to build up. But the point is that these kinds of assumptions, if you try mean field, it's just kind of you're just doing it by fiat, right? You don't really know that your system is strongly correlated or not. And so the point is that these types of studies in the past just might fundamentally miss some interesting and important many-body effects. And so that's kind of one of the questions that we had going forward. to try and explore the possibility of true many-body physics more deeply. Let me kind of give one slide to explain exactly how an optical lattice clock works, or even just even a single atom clock. So the technique that people use is so-called Ramsey spectroscopy. Okay, that's basically the standard in atomic spectroscopy. And the idea is the following. So initially, you have an atom in the ground state. At time equals 0, you do a pi/2 pulse on the Bloch sphere. So you bring your atom into equal superposition of ground and excited state. And then the point is that the laser that you use to bring the atom up to this superposition state, your laser has a well-defined frequency, omega L. And so the point is that in a realistic laser, that laser frequency can start to drift. Okay, so if the laser frequency was always perfect, that would already be your clock, right? But in a realistic system, your laser frequency would start to drift around. And what you're trying to do is you're trying to reference that drifting laser frequency to hopefully the fixed and robust atomic resonance frequency. And the way that happens is that if you move into a frame that's rotating with the laser frequency, then the atom, which only knows about the kind of its own natural resonance frequency, then on the Bloch sphere, what it causes is it causes a precession of your state along the equator. Okay, so your Bloch vector starts to precess at a frequency that's given by the difference between your laser frequency and the atomic resonance. So this kind of precession, or this kind of coherence on the equator, is not necessarily easy to measure directly. But then one way to measure it is actually then at a later time to do another, let's say, minus pi/2 pulse. And what that does is that maps that precession on the equator to a population difference between the ground and excited states. And population in ground and excited states, that is very easy to measure. So as a hypothetical example, imagine that the laser frequency and the atomic resonance frequency happen to perfectly match. Then your state would not precess at all during this time. And so you did a pi/2 pulse, and then at a later time you do a minus pi/2 pulse. That just brings you back down to the ground state. On the other hand, imagine that there was a frequency difference, and then at some magical time, this state precessed halfway around the equator. Now when you do this minus pi/2 pulse, you map that coherence up to an excited state population. So measuring ground state versus excited state population as a function of time, that informs you of the difference between your laser frequency and the atomic resonance frequency, and then you can try to feed that information back to correct the laser frequency. So then now your laser frequency ideally is locked to the atomic resonance. So if it's an independent atom, then there's a limit of how long you can wait between the first pulse and the second. In particular, you have to kind of complete this sequence before the natural spontaneous emission time. Otherwise, your atom would just always be back in the ground state. And when you do that, that leads to a so-called standard quantum limit of how well you can resolve the frequency, or how accurate your clock can be, as a function of the total time of your experiment. Okay, so that's the kind of story if you had a single atom or n independent atoms. Are there any questions about that?
One question. I would say, the pi/half pulse is not the limiting factor as well. Like, how could you know that you're doing actually a pulse that has that duration? Like,
yeah. So the beauty of this Ramsey spectroscopy is it's actually very robust. So even if it wasn't perfectly pi/2, the story still holds. So that's what makes this that's one of the reasons why this Ramsey spectroscopy technique is actually so beautiful. It's actually very robust to any number of imperfections that you can experience.
Thank you.
Maybe as an aside, so another reason why this Ramsey spectroscopy is robust is, so to tell what the resonance frequency of the atom is, you inevitably have to shine in light or excite atoms somehow. And the first thing you would imagine if you build a clock is, well, let's just always shine in light and excite atoms and look at fluorescence. But then the problem is that you have light coming in all the time. The light could actually interact with your atoms, introduce shifts in some non-trivial way. And so the beauty of this Ramsey spectroscopy is you just do a very strong pulse at the beginning, and then your atoms see nothing. So they're really sitting in vacuum, evolving on their own. And then at the end, you shine a second pulse. So the amount of time that the atom actually sees the laser is infinitesimal. So it's a really beautiful idea for spectroscopy. So this idea that maybe your system actually turns into an interacting system via these dipole-dipole interactions, that's actually an experimental fact now. Okay, so it's not some theory idea. Just in actually this year, people have been able to build optical lattice clocks in 3D lattices, where they see essentially so if you have independent clocks, it shouldn't really matter the details. So if I shine in light this way to excite an atom versus that way, shouldn't matter. If I excite one excited state versus another excited state, shouldn't matter. And what they see is that it does matter. So what I'm plotting here on the vertical axis is the change in the apparent resonance frequency of the atom when they do this Ramsey spectroscopy as a function on the horizontal axis of some variable of the experiment, like the direction that you shine in light. And you see that these shifts are very small. So the kind of apparent resonance frequency is shifting on the order of a millihertz. But a millihertz is enough to see these days. So it is at the 10 to the minus 18 level. Okay, so here's just one example where they shine in light from two different directions. If you do a theory at early times, where before the system potentially gets strongly correlated, you can actually predict what these shifts should be. So they see that if there's one direction you shine in light, the shifts should be very minimal. But then there's another direction where you shine in light, the shifts amplify. And they can really see the difference between these two cases in the experiment. Okay, so at least so far, there's kind of good agreement with perturbative theories. But then you can ask, is it possible that future experiments would go beyond this kind of early time stage, get more correlations? And then if that's true, how can we possibly even understand what happens, and how well can we actually trust the clock in that potentially strongly interacting regime? So I think the 3D lattice is potentially very complicated. So we try to do something a little bit more modest, something that's a little bit more amenable also to numerics. And so we'll just kind of invent a toy lattice clock. Instead of working with 1 million atoms in 3D lattice, let's work with some manageable number of atoms, just sitting on a 1D chain, but living in 3-dimensional space. And so this type of system we already discussed yesterday, at least in this single excitation limit. I convinced you that this type of system can act as a waveguide for single photons. Okay, so if you have one excitation, it's possible that that excitation actually lives forever, at least if this chain becomes infinitely long. So then the hope is that with this kind of system of reduced atom number, by some means, numerically, theoretically, or maybe experimentally someday, can we somehow gain insights on what this kind of toy model lattice clock would do, in hopes of eventually tackling the original 3D problem. Okay, so that's the kind of goal of this project. So let me just show some kind of numerical results. First, the numerical results are either done by straightforward exact evolution of these density matrix equations, or by some fancier matrix product state simulations. So what we'll do is really try to model this kind of Ramsey sequence. So we'll pretend like this was an experiment. We're just going to try the Ramsey sequence and see what the effect is of these dipole-dipole interactions. So first, let me show you some numerical results, and then I'll try to come back and give some interpretation of what's going on. So in the Ramsey pulse, remember the first thing that you do is you excite half the atoms in a superposition. So you do this pi/2 pulse. And then what you can do, so you do that at time 0. So you create some atomic excitations. Here I'm plotting the number of atomic excitations on this vertical axis. And then what I'm going to plot in time is the total excited state population as a function of time. So if it was independent atoms, that population would presumably decay exponentially. And we could try to look for corrections to that. So what I'm showing here for the different colors are just different atom numbers going from 6 as the blue to up to 30. And one thing you can already notice on this plot here is that it's evidently, as you go to larger atom number, at long time, it's evident that that decay is no longer exponential. Your population is not going to zero exponentially, but somehow it's hanging around in your system. So that kind of looks like this subradiance that we talked about yesterday. You can take the same plot and you can replot it on a log-log scale. And what's kind of evident at long times for large system sizes is that you get this kind of straight line on a log scale, which means that the population isn't even decaying exponentially anymore, it's decaying as a power law in time. And if you fit it, it turns out to go like 1 over square root of time. So the fact that you've changed from an exponential to a power law, that certainly indicates that your system is certainly not a set of independent atoms. There's some type of interactions that are building up in your toy model of a lattice clock. Another thing you can do is then after you wait some time, you can close the Ramsey sequence by applying this second minus pi over 2 pulse. And so what I'm plotting on the color scale here is basically the population difference between the excited and ground states. So you would expect that that has a kind of oscillatory behavior in time because you're processing around the Bloch sphere. But what you see is that there's also some kind of non-trivial dependence on delta. Okay, so if it was interacting systems, then there should be no kind of features along a fixed direction. But you see that there are, and that kind of infers that from that you can infer that there are some type of interactions. If you plot the kind of this kind of fringe here, this is the kind of resonance frequency, apparent resonance frequency of your clock. So if you did the experiment, if you track this fringe, that's kind of like your apparent resonance frequency. So ideally, you want your resonance frequency in your clock to be independent of time, right? And the fact that it's shifting, so it's like its time is apparently accelerating, it means again that your clock is an interacting system rather than being independent. Okay, so your definition of a second at this time would be different than your definition of a second at a later time. Okay, so that's not really what you want from a clock. Maybe the most interesting thing is you can ask, well, one way to try and measure correlations is looking at where are my atomic excitations sitting. So you can numerically go look at density-density correlations. So if I know that atom M is excited, what's the relative probability that atom N, some distance away, will also be excited. And so if it's independent systems, then this correlation function should be featureless. And that's what you see at early times. But then as you let the system evolve further and further in time, what you see is that there's a kind of dynamical growth of correlations. And these correlations tend to have quote-unquote fermionic character, or at least some sense that excitations are trying to repel each other. And the way you can kind of tell this from the plot is, here's a plot, I guess, of, 12 or 14 atoms. And what we see is that, the density-density correlation has a peak here, which kind of says that if atom 4 is excited, then it's very likely that atom 12 is also excited. So there's certainly some non-uniformity, and it seems like the excitations are trying to avoid one another. So that's what we numerically see. And now I'll try to provide at least some partial explanations of what's going on. Any questions on the numerics?
So just quickly, in this B panel, is this the connected expected value, or why?
Oh yeah, sorry, it's the, right, I should have. No, it is, so for off-diagonal elements, it truly is this thing.
Yeah.
For the diagonal, we just artificially set it to zero. So yeah,
Okay.
it shouldn't be written sigma EE. Sigma,
All right.
like
All right.
this just says this is meant to illustrate that you can't excite a single atom twice.
So you do ED kind of simulations for these sizes.
Yeah, some combination of well, right. So we do exact numerics up until about 16 atoms, and then to reach 30, we switch to matrix product state dynamics. Okay, so just to kind of build up a little bit of the physics, let me remind you of what we discussed yesterday. If I have a 1D chain and just one excitation, then we argued yesterday that you can have, in principle, perfect subradiants. So there's some spin wave modes whose wave vectors are bigger than omega over c, so they decouple from radiation fields. And then those modes should have an infinite lifetime. So that's what you can kind of plot here for different polarizations of the atomic transition. In any case, if the wave vector, the block wave vector is too big, the decay rate is 0. And then when it's so-called within the light cone, the decay rate is non-zero. Okay? And that you can interpret as kind of your atom chain acting as an optical waveguide or optical fiber. Again, remember that if we now go to a finite size system, numerically what we see is that the decay rates of the longest lived skates, they scale like 1 over number of atoms to the 3rd power. And then if you index the eigenstates by 1, 2, 3 in order of increasing decay rate, then the most subradiant state would have a decay rate 1 over n cubed. The second most subradiant state would have a decay rate 4 over n cubed, and so on. Okay, and physically, the reason in a finite size chain that you have a decay rate is because your optical fiber guides light until the light hits the end, and then it scatters into free space. Okay, so this kind of single excitation physics or this wave guiding is totally classical, so you can understand it just by classical optics. The first thing you can ask is, well, if I have more than one excitation, how can I understand subradiants in that case? Do subradiant states exist? And if so, what kind of physical characteristics do they have? So let me introduce just a little bit of definitions. So let me define, for a finite size system, a spin wave creation operator, S1 dagger, where this index 1 is exactly the index in terms of subradiant states. So this S1 dagger, its effect on the ground state is exactly to create the most subradiant single excitation state. So then you can ask, well, what if I try to create 2 excitations in the same mode? So what if I just try to apply this spin wave creation operator twice on the ground state? You can ask, is that subradiant and is it an eigenstate of the system? So if we're talking about harmonic oscillators, the answer is yes. So 2 excitations would then simply have a decay rate that's twice that of a single excitation. So a harmonic oscillator, if you have 10 phonons versus 1, the 10 phonons, of course, dissipate 10 times faster. But since we're talking about spins, 2-level systems, it's not an eigenstate. And the way you can kind of understand that is the following. So let me just kind of write out this 2 excitation state in this basis of atom I being excited and atom J being excited with some amplitude Cij. So if you just kind of numerically plot out Cij squared, so this gives you the relative probability that atoms I and J are excited, you get a shape like this. So it's relatively smooth with a diagonal cutout, which simply says that you can't excite the same atom twice. Okay? And the point is that you have this kind of, so in position space, you have this very sharp spatial feature. But remember that the decay, the ability of atoms, excited atoms to emit light, that you should really think of in momentum space. Right? So high momentum modes do not decay, low momentum modes do decay. And the point is in real space, anytime you have a sharp spatial feature, the fact that one atom can't be excited twice, when you Fourier transform any type of discontinuity, you get a huge range of k vectors. So just the fact that you can't excite a single atom twice means that this state has a lot of wave vector components within the light line. So then if you numerically calculate what is the decay rate of this state, it no longer scales like 1 over n cubed, but it's actually jumping up to 1 over n, physically because, again, it has all wave vector components. So then based on that intuition, you might ask, well, is it, can I try to by hand construct a few excitation subradiant state? And the intuition you should follow is that if you really want a subradiant state, on one hand, you should think of it in k-space. So in k-space, you should make sure that your wave function only has wave vectors that are bigger than omega over c. But then you should also think of it complementary in real space. You should avoid spatially overlapping excitations, right? Because then, that's the problem that I showed before. If two excitations try to touch each other, they notice that they can't excite the same atom twice, and then you naturally get all these Fourier components at once. So how do you naturally satisfy both conditions? Well, you can try to create a Slater determinant of your single excitation wave functions. So as an example, imagine that I take, again, 1 and 2 are labels for alpha. So Ci1 are the wave function amplitudes for my single excitation amplitudes for my most subradiant state. C2 are my excitation amplitudes for my second most subradiant state in the single excitation manifold. And then what I can try to do to create this 2 excitation state is create a Slater determinant, which basically builds in Pauli exclusion. Okay, so the fact that I'm taking the 2 most subradiant states, that guarantees that in k-space, they really have k vectors that are beyond the light line, and this minus sign, this Slater determinant, guarantees that there's a kind of repulsion between these excitations, so they can't physically collide. So then the wave function you see looks smooth in position space. You avoid this kind of sharp kink. And then what you find numerically is that the decay rate of this 2 excitation state is more or less the sum of the decay rates of the single excitation state. So now the fact that you created this Slater determinant makes the scaling of the decay rate, again, drop to 1 over n cubed. Okay. So this is just intuitive ansatz, intuitive guessing. But then when you look at numerics, you compare this ansatz with numerics, you see it's actually a very good guess. And even though I presented the ansatz just for 2 excitations and for the trying to find the most subradiant 2 excitation state, what we can show numerically, or as far as we can check numerically, this kind of ansatz is true in general. So anytime your number of excitations is much smaller than the number of atoms, the most subradiant states seem to be built out of a Slater determinant of single particle states. Okay, so you can take that as our current understanding of how multi-excitation states manage to be subradiant and hide themselves from spontaneous emission. And the fact that the longest lived states happen to look fermionic, that kind of qualitatively explains what we see in simulations, this growth of fermionic correlations in the density-density correlation function. So from these arguments, you can also create a plausible argument of why you get a parallel decay of the total excited state population as a function of time. The fancy word for it is you have a closing Liouvillean gap. But the picture is basically the following. So imagine I had have a set of eigenstates with a decay rate, with a distribution of decay rates gamma. So if I chose a certain eigenstate, it would decay like e to the minus gamma t. But one thing I know is that that decay rate in the thermodynamic limit can go to 0. Okay. So if I were to take my excited state population as a sum over a bunch of states, my lower bound goes to 0 because I know that there are states in the thermodynamic limit that live forever. And then your total excited state population would be, you take each of these states, you look at their density of states, which based on 1D, you can easily conclude it has a gamma to the minus 1/2. And then, for example, if you assume in the dynamics that all these long-lived states are populated in a uniform manner, then when you do this integral, you exactly get 1 over square root of t. So it's not a proof, but it's just some kind of plausible argument of how a power law decay can emerge. So let me kind of show numerically that this kind of smooth distribution seems to be true. So what I'm showing here is actually kind of different snapshots of the dynamics. So we have 12 atoms. So on the vertical axis, I'm ordering all the eigenstates by the number of excitations. So 0 is the ground state, n equals 12 is the full excited state, and I have the 1 excitation manifold, 2, 3, and so on. And the way I'm ordering these eigenstates is by increasing decay rate going from left to right. And so what I'm showing here is simply kind of numerical simulations where we ask, as the system drops from the fully excited state to the manifold where n minus 1 atoms are excited, when it drops, what's the probability distribution to populate any eigenstate? And you see that at first, when the population decays, you tend to populate the fastest radiating states. But then as you start to fall down the ladder, then the population distribution starts to re-equilibrate itself and could become highly balanced. So by the time you have a few excitations left over, you said that you are indeed populating all the subradiant states in an equal fashion. So this is a heuristic, again, a heuristic argument of why a power law decay might emerge. One thing you can also check is, to get a flavor of, how strongly correlated is the dynamics or how complex is the problem to solve. One thing you can do is you can try to check numerically. You can compare the exact numerical solutions with some approximation, like mean field or so-called cumulant expansion. Cumulant just means that if you have some kind of complicated correlation function involving, let's say, 3 particles, you try to assume that you can decorrelate it into just pairs of particles. And what we see is that these types of mean field or cumulant expansions don't seem to agree well with numerics. Okay, so the blue here is just the excited state decay as a function of time by exact simulations. The red is a cumulant expansion. You see the population decays way too fast. It doesn't really reproduce this kind of power law. One thing you can also check is, well, is it, the fact that this cumulant expansion isn't working at late times? Maybe it's just because at early times, maybe it doesn't work, and then I'm just kind of propagating errors forward. But it seems like that's not the case. So another thing you can do is you can run the exact dynamics up until some time t. Then you turn on the cumulant expansion. So you only start your approximation at that time t. You again see the cumulant kind of runs away from you. And so you can try that at different times. The cumulant solution always runs away. So there seems to be some kind of flavor of correlations in the dynamics, in the density matrix, that a mean field or cumulant expansion is not able to capture. Okay. So then how do you capture the dynamics? Honestly, I don't know. I think that kind of hints at a little bit, already gets to some kind of frontiers of what we actually know about these spin models in the many-body regime. So it's really an outstanding challenge to develop a more proper theory for this type of open many-body dynamics. Okay, so I try to give one example of the spin model and correlated dissipation in the many-body limit. You show that this example is not necessarily esoteric. So these kinds of questions are also tied to real applications, like trying to build the best frequency standards and really understanding what kinds of errors can pop up. And then as the kind of last thing I'll discuss, so I don't think I'll be able to discuss this third example of number sorting. So the second example, which I like to bring up, is something that I also brought up yesterday. Why is the refractive index of real materials seemingly so small? And remember that I gave you a challenge. If you can find a material with a refractive index of 10, I'll buy you lunch. So I think no one has satisfied my challenge so far, but you still have 1 hour to find one. Okay, so in case you're too lazy to to take on my challenge, let me at least here's my own attempt to answer my challenge. So if we look at real optical materials, so we're not talking about atoms anymore, but really just solids. We can look at, for example, what's the refractive index of transparent materials in different wavelength ranges. So for example, if we say that we want a material which is transparent in the mid-IR, so 5 microns, here's some representative materials, and you see the kind of highest number of refractive index among this set is about 6. Okay? And then empirically what we know is that when we go to higher and higher frequencies or lower wavelengths, those refractive indices start to drop. So by the time we get to visible, so materials that are transparent at visible wavelengths, that's the blue set, the biggest index seems to be somewhere around 3. If we then want a material that's transparent at ultraviolet, again, well, you see the pattern is that the refractive index drops, and the highest, again, value is around 2.5. Okay, so at least empirically, the refractive index of real materials seems to be of order 1, somehow irrespective of any kind of underlying details of the material. So whether it's disordered, ordered, gas, solid, etc. And again, that's very different than any other material property you can think of, conductivity, specific heat. So that can vary by orders of magnitude. So it really just opens the question, like, why the heck is refractive index always the same? Aside from just being a kind of weird observation, it's also very important for optics. So I would say in classical optics or photonics, refractive index is the most important resource that we have. And one reason for that is, among other things, refractive index describes how much you can shrink the wavelength of light in a material relative to vacuum. And so having an ultra-high index directly translates into how small you can make optical systems, what's the minimum size of an optical waveguide, for example, that you could fabricate. It also dictates the minimum length scales that light is able to access. Let's say for microscopy, for lithography, what's the smallest feature that you can define, etc. So I don't really know how to scientifically quantify this, but I would tend to believe actually that if we could find an ultra-high index material, it would actually be more valuable economically than having a full-blown quantum computer. So that's my guess. If someone knows how to quantify that, I'd be happy to listen to your argument. Okay, so it's just kind of weird observations period, but then if you come from quantum optics, and even like my first lecture, my introduction, then you can easily cook up an argument that is super weird, okay? So in particular, remember that the foundation of quantum optics or atom-light interfaces is that if you have a single atom and you shine in resonant light, your atom has a scattering cross-section that's given by the wavelength of the transition squared. Okay? And what's kind of weird about that result is that a typical transition wavelength of an atom is 1 micron, but the physical size of the atom, or if you want the physical size of an electron wave function, is the Bohr radius, which is a fraction of a nanometer. So what that says is that your atom is not scattering light like its physical size, but it's scattering light as if it was a much bigger object. Okay, imagine something like a tennis ball casting a shadow that's as big as a building. Okay, that's the analogy. Okay, so then you can play the following thought experiment. Let me make up a material, which is just a cubic wavelength sized box. And it's vacuum, but I put 1 atom in that box. So I explained to you that 1 atom can have a non-trivial or a phase shift of light, can induce a phase shift for near resonant light. That's not arbitrarily small, right? You can get some fraction of a radian. And so then, however you want to define refractive index, you would conclude that the refractive index of this made-up material is already reasonably different, noticeably different than 1. And then, no matter what field of optics you come from, or no matter what version of an electromagnetic textbook you read, you always have the notion of collective enhancement or multiplicative effects. Okay, so the more atoms or the more material I have, the more optical response or the bigger the index. So then if I don't put one atom in, but I put 10 or 100, shouldn't the refractive index of this material already be much larger than 1? And the point is that when you have 10 or 100 atoms per cubic wavelength, that's still orders of magnitude more dilute than an optical solid, than a realistic solid. So that's the kind of thought experiment you can cook up. And then you can just really go to the textbook and ask what is the refractive index of a collection of atoms or molecules. And so that's the entire field of macroscopic E&M. There's any number of formulas you can look up in a textbook, but basically what you take is you take inputs, what's your particle density, and what's your polarizability of your atom as a function of frequency, and then your textbook will spit out some refractive index as a function of frequency. So there's different formulas that you can find in electromagnetic textbooks. You might remember the so-called Drude-Lorentz model of refractive index. That model says that your index scales like square root of the polarizability times the atomic density. You might also be familiar with the so-called Lorentz-Lorenz model, which attempts to correct for the fact that when you have a lot of atoms, an atom actually sees some corrected near field or local field coming from nearby atoms. In this particular Lorentz-Lorenz model, what you say is I have one atom, and I'm going to approximate the effect of all the other atoms, so the field being scattered by all the other atoms. I'm going to approximate all the other atoms as a smooth material, as a refractive index. And then I'm going to self-consistently calculate the refractive index. So the details of that model don't matter. The point is that when you apply this Lorentz-Lorenz model for atoms, you get exactly the same refractive index as the Drude-Lorentz model, but just with an overall shift in the spectrum. Okay? So that's to say that both of these models give you the same maximum refractive index. So the problem then is the following. So it's a fun calculation. You can take you look up the polarizability of an atom that anyone uses in the lab, rubidium, cesium, etc. You take a value of that polarizability near resonance. So you can find these numbers in 5 to 10 minutes on the internet. And then you can plug it into your favorite formula for refractive index in your favorite electromagnetics textbook. That takes you another 10 minutes. You can plot out what's the maximum refractive index. So maximum means at some optimized frequency, so presumably somewhere close to the atomic resonance. What's the maximum refractive index you expect as a function of atomic density? And the textbook answer will give you something like this. So as you increase the density of your material, by the time you hit the density of a realistic solid, that formula will predict a refractive index of 10,000 or 100,000. Okay, so it's amazing, right? Because it's a calculation you can do in 10 or 20 minutes, starting from any one of your favorite textbooks. So your textbook says a material should have an index of 100,000. And Jackson never says why that's incorrect. It never says that these formulas are incorrect. And so it's just kind of a complete mystery what is going on. Of course, we know empirically, at least, that the real answer, once you go to the density of a solid, is that the refractive index is close to 1. And so you compare this point here, this curve here. There's no obvious way to reconcile that. Just for reference, cold atom experiments, degenerate quantum gases, they sit somewhere in this regime here. If we're going to be kind of fully honest about the question, we should also acknowledge that at some point this kind of textbook calculation has to break down. Okay, because so the textbook assumes that you have really point-like scatters. So that's what we might call the quantum optics model or the spin model, where we really assume our atoms are point-like. At some point, of course, when the atoms get very, very dense, so the nuclei between nearest neighbors gets very small, then of course the nuclei start to notice that the electrons really know that they're not point functions, but they really have some spread. So that's just to say, electronic orbitals have some finite size, the Bohr radius. And so once two nuclei get too close, then when these orbitals start to overlap, that's when kind of what you might call quantum chemistry or solid state physics would turn on. Okay, so once that quantum chemistry turns on, your textbook should start to break down. But still, you have the issue, you don't really know what's the proper curve going from this regime here of cold atoms to a real material. So the questions then to ask are, is it possible to actually draw a curve between these two limits? What would it look like? What's the physics governing that curve? And if we're lucky, is there maybe a non-trivial maximum refractive index you get somewhere in between that's noticeably bigger than 1? Okay, so that's the kind of goal. Are there any questions on that? Okay. So what's wrong with the textbooks? Well, based on the lectures that I gave so far, you might be able to take a guess, which is it's the whole problem of multiple scattering and wave interference. So in particular, if you look at this formula here, it just directly scales with atomic density, irregardless of the microscopic details of the system. Right? This formula doesn't say that if it's ordered versus disordered, the answer might be different. If it's disordered and you have two different configurations, the answer might be different. And the fact that it just kind of scales directly with density, it means you're kind of implicitly taking kind of like a particle-like view of light. So light is something like a tennis ball. It has a chance to hit the first atom. If it misses, it can hit the second atom. If it misses, it can hit the third atom, and all those responses just add up without any kind of phases. Okay. And of course, the whole story of these lectures is that the real problem is that when light shines in, when you shine in light, you get a wave phenomenon of multiple scattering and wave interference. So that in itself is not a deep statement, but again, the kind of complexity that we see coming from quantum optics is that an atom has a very big scattering cross-section on resonance. So once the distance between atoms becomes smaller than a wavelength, you might expect that this multiple scattering problem becomes highly non-perturbative. And we already saw examples of that. Okay, so then you might expect that if you want to answer this refractive index problem, there's at least two different limiting cases. In one case, you could say maybe the atoms are completely disordered, like an atomic gas. In the opposite case, you have a crystal, or the atoms are perfectly ordered. And for now, let's just restrict ourselves to the quantum optics limit of point scatters, which means that you can literally apply this kind of Green's function spin model formalism to this problem. And we're only interested in linear refractive index, so it suffices to just send in one photon and look at the response. So the complexity is not 2 to the n, but just linear in the number of atoms. It turns out that you can understand most of the answer just from an understanding of the problem of two atoms, which are very close together. So that was actually one of the exercise problems that I gave you. And so the main points of the solution are the following. So you could ask, for example, if I have two atoms and I shine in light, what's the spectrum of the scattering cross-section as a function of the frequency of the light that you send in? And remember, just to normalize the discussion, if I have a single atom, I expect a Lorentzian response that's peaked around its resonance frequency. And the scattering cross-section on resonance should be lambda squared. And the point is that when you have two atoms, which are very close together, the answer is not simply double that of a single atom, which is kind of what the textbooks would imply, but you actually get two very well-separated Lorentzian peaks coming from the fact that you have two normal modes of the system. So the dipole-dipole interactions, or the multiple scattering, lead to some interactions that lead to two normal modes with very different resonance frequencies. So these normal modes are, if you want a classical interpretation, one normal mode is you have two dipoles that are oscillating in phase. Another normal mode is that you have two dipoles that are oscillating out of phase. And if you manage to go through that exercise, you would have seen that as the distance between atoms goes to 0, the splitting between these two resonances goes like 1 over r cubed. And that 1 over r cubed is coming from the near field interaction of these two dipoles. So now the key idea is the following. So on one hand, I try to explain that this phenomenon of normal mode splitting is coming because you have two identical atoms which are close together and therefore very strongly interacting via the near fields. But then if you look at this kind of plot here, you would say, well, it's just two Lorentzians, right? Like, why do you need that kind of complicated description? So in particular, if I just gave you from the very beginning two atoms with two very different resonance frequencies, and with the near field interactions turned off, if you calculate the scattering problem, you get exactly the same answer. So in the far field, there's no way to tell these two systems apart. So it's this idea of equivalence. These two strongly interacting identical atoms are optically equivalent to two atoms with just different resonance frequencies to begin with. So you can now take that idea and try to understand the refractive index of an entire disordered medium. So the point is that if your atomic positions are random, then statistically there will be some pairs of atoms which are very close together. And if they're very close, that means they interact very strongly via the near field. And in fact, they interact so strongly that you can take this Green's function. So in principle, every atom interacts with every other atom. But then you can try to treat it in perturbation theory. In other words, you can say that this pair, to lowest order, only interacts between itself, and every other atom is just a perturbation. Okay? So then if you take this perturbative approach, then you're just trying to solve this 2 by 2, this interaction between two atoms. That's exactly what I showed you before. And so the point is that you can replace these two atoms with two different atoms with different resonance frequencies. And the point is that the splitting, the difference between these two resonance frequencies, that scales like 1 over r cubed. But when you have a disordered medium, r itself is a random function. So this omega plus and omega minus, they take on a non-trivial distribution over values. And then qualitatively, the idea is you can continue this argument over and over again. You take these two atoms, you replace them with two new atoms. And then you can go find the next most strongly interacting pair. You diagonalize, you replace by two new atoms of different resonance frequencies over and over again until you have no near field interactions left over. And again, this final system should be optically equivalent to your original system. So here's a picture of what, and there's a fancy word of that. So this procedure is formally known as strong disorder renormalization group, but it's nothing more than this kind of cartoon picture I'm illustrating here. Okay, so what's the final result? Well, our original system, again, is formally all the atoms are identical. So the distribution of resonance frequencies is just a delta function. And I have very strong near-field interactions. And then at the end of this renormalization group argument, I say that I have an optically equivalent system where I now have a distribution over resonance frequencies. And again, the kind of distribution over resonance frequencies, or the width of the resonance frequency distribution, you expect that scales like 1 over r cubed, where r is the characteristic nearest neighbor separation. And in the 3 dimensions, 1 over r cubed for nearest neighbors is directly proportional to the density. Okay, so the point is that this distribution is just scaled directly like the density. And then you can see this actually numerically. So here what I'm plotting is the distribution function of resonance frequencies rescaled by the density itself. So frequency is divided by density. And you see that regardless of density, all these curves collapse onto the same one.
So, but why should I expect that curve to be Lorentzian? I mean,
which one?
The collective one, when you sum over all disorder.
Oh, this
stuff.
one?
Yes. I mean, I see, okay, the single particle at the beginning are Lorentzian, but then shouldn't this know somehow of the disorder correlations?
Yeah, so it's actually not Lorentzian. So
okay.
yeah, I mean, it's some curve, but.
Okay.
Right. So I think the tails are Lorentzian, but the peak is not. And the point is that this is a non-perturbative treatment of near fields, because I'm trying to take this very strongly interacting Green's function matrix, and I'm finding a clever way to approximately diagonalize it over 2 by 2 blocks. Okay, so if you believe that argument, then now you can also already qualitatively understand why the refractive index of a disordered medium might not be arbitrarily large. Go ahead.
But if the density is high, could it be possible that, for instance, you have to group in 3 pairs? Like, I mean, this RG procedure that you do, did you test doing different groups, instead of pairs, 3? Does it change?
Right. So it's a hard question to quantitatively answer. If you try to kind of plot things like kind of marginal distributions and so on, what you find is that the likelihood of so the point is, because the interaction is 1 over r cubed, the fraction of pairs where okay, you have 2 atoms in a pair, and then the third atom is close enough that it's 1 over r cubed actually significantly modifies the eigenstates. Those tend to be kind of a marginal set of all possibilities. So then, again, these are things that are very hard to prove, but it seems like the kind of triangles and so on shouldn't really matter in the qualitative answer.
But this is like, you can justify this saying that you're working at intermediate densities, because at super high densities, you're expecting that this should break down because you are into the quantum chemistry realm. Right. So this is a possible.
So if we only talk about the near field, then it should actually be invariant, because there's no other. So you have an interaction that's 1 over r cubed, but you have no other scale. So you expect some kind of. It shouldn't be a. Right. So the statement is that when you do the RG, only assume for the moment you only have the near fields, then it should actually be kind of scale invariant.
Okay. Thank you.
Okay, so now let's go back to this kind of made-up material. So I have a cubic wavelength size volume. I can put 1 atom in 10, 100. And the point is that no matter how many physical atoms I put in, so if I put in 10 atoms, that's fine. But I know my broadening of the resonance frequencies scales up by a factor of 10. I could put in 100 atoms, then my distribution of resonance frequencies increases by a factor of 100. So that means that when I actually shine in near resonant light of any given frequency, on average, per unit volume, per wavelength cubed, that light only sees, on average, 1 resonant atom to talk to. So all the other atoms have been physically shifted far off resonance. And so if you only talk to the same number of atoms, regardless of the number of physical atoms, then you can believe that that limits the optical response. It limits the refractive index. And in fact, you can kind of do that calculation more carefully. So if you believe in this renormalization group argument, when you now re-examine the maximum refractive index as a function of density, you see that this renormalization group argument predicts a maximum index of 1.7. So that's kind of neat. It's a very minimal model, but you get back a real-life answer of refractive index. And furthermore, this kind of electrodynamical effects, it kicks in around a few hundred atoms per cubic wavelength. So this is way before any type of quantum chemistry has turned on. So the message seems to be that if you have at least a disordered material, the reason that its refractive index is of order 1 is all derived from this dilute electrodynamic regime here. And you can compare with exact numerics on the spin model. The numerics line up very well. Again, the full numerics also predict a maximum index of 1.7. And finally, if you believe everything I told you so far, you can also believe why it's actually very subtle for a textbook to get the right answer. Because anytime you develop a macroscopic theory of light or of optics, so you're trying to kind of coarse grain or smooth away the microscopic physics, it's that kind of smoothing that actually kills you. So once I say I can approximate my atoms at a smooth density, that's where the textbook goes wrong. Because what you learn from this renormalization argument is that single nearest neighbors matter a lot in the optical response. So the only way that you possibly get the correct answer in a macroscopic theory is actually to keep the nearest neighbor explicitly and then do the smoothing operation. So that was the case of disordered atoms, and now we can move to the case of a fully ordered crystal. And to try to understand the refractive index in this case, let's again start in the quantum optics limit where the distance between atoms is much bigger than the Bohr radius, which means we can use our spin model again. And so to understand the refractive index of a 3D lattice, we can actually, all the physics is actually encoded in this problem that we already studied, which is that a 2D array can in principle act as a perfect mirror for light. Instead of talking about a perfect mirror, let me change the wording just a little bit. So let me say that a 2D array exhibits a lossless single mode response to light. And let me explain what single mode means. So if we take an infinite lattice, we shine in light as a plane wave. It means that on one hand, this plane wave does not see these atoms as n independent degrees of freedom. But because the light is exciting the atoms with all the same phase, I only excite one collective mode, where again, all the dipoles are radiating in the same phase. So single mode in the sense that I excite one very specific eigenstate of the system when I come in with a plane wave. It's also single mode in a complementary sense, which is that once this set of dipoles starts radiating in phase, the light that emits is not in completely random directions. It's back in the same single mode of light that I send in. So that's just to say if I shine in light straight down, when this object re-radiates, it's going to re-radiate either light back down or straight back up. It can't radiate into a random direction, right, because this is a diffraction grating. And I've shut off all my diffraction orders. And the photon can't disappear because it's an isolated atom, so there's no internal degree of freedom of the atom to just eat the photon. Okay, so that's what single mode means. I shine in light, it excites one mode, that mode re-radiates all the light back into the mode of light that I sent in. It's a completely classical effect, but if you want to kind of draw a quantum type level diagram, you can think of it as the following. I have a total ground state, I shine in light, I excite just one normal mode of the system, and that normal mode, the only way it can decay is by radiating a photon back in the same mode that I sent in. And again, we already know the consequences of that. You can look at reflection and transmission as a function of detuning. On resonance, you get the 100% reflection. More important, though, for this refractive index problem is that if you're not exactly on resonance, you have some amount of light that's transmitted. But it's transmitted with a very large phase shift on the order of pi. So remember that this pi phase shift is something we derived for this kind of perfect chiral waveguide. And that feature persists even for the 2D array. One important thing is actually if you calculate what's the line width of this resonance, it's not the single atom line width because all the atoms are radiating in phase. So you have a very strong constructive interference. So in fact, this collective mode is radiating light at a rate proportional to the single atom emission rate times lambda over d squared. So as you make the lattice constant smaller and smaller, this mode radiates light more and more efficiently. And that actually makes this effect robust to certain imperfections, including those which arise from quantum chemistry, which I'll explain in a little bit. Okay, so with that, we can already qualitatively argue what the index of a 3D lattice would be, because we can simply divide conceptually our 3D lattice into a bunch of 2D arrays. Okay, so I have a single 2D array. I shine in light. Some light is transmitted if it's near resonance with a very large phase shift. And then I hit the second array. I acquire another big pi phase shift, and so on. And refractive index is nothing more than how fast you accumulate phase shift. So if I accumulate a phase shift of pi every lattice constant dz that I propagate, then my refractive index is actually just lambda over dz, and that's proportional to the density of atoms to the 1/3 power. So there's a couple of things to take away. So at least in the quantum optics limit, as you increase the density, the refractive index continues to grow indefinitely. It grows at a slower power, 1/3 rather than 1/2, compared to what the textbooks told you. And even more importantly, Because this is a single mode system, so I shine in a photon, the photon can't disappear and it can't scatter into another mode. This refractive index is purely real. Okay, so there's no absorption in this system, at least at the level of idealization that we have here. Okay, so again, the key physics is all derived from this single mode nature of atom-light interactions in 2D arrays. So it's a kind of, I mean, this is not a very important point, but it's a kind of cute argument or calculation you can do. So you can say that, well, inevitably at some point, my point scatter picture has to break down. An upper limit would be that, okay, when the lattice constant is the Bohr radius itself, clearly quantum chemistry has already come in. And so if you plug the Bohr radius into this formula and just do some basic atomic physics, let's say for the hydrogen atom, then you find that the maximum refractive index that you could ever have in a material is proportional to 1 over the fine structure constant. Okay, so that's already a hint that Jackson has to be incorrect because it's predicting 100,000 rather than 1,000. So it turns out the real answer is not nearly that good, okay? But that's a kind of cute loose bound that you can derive from very simple arguments. Okay, so what do we have so far? Let's go back to this kind of plot of refractive index versus density. The textbook is completely off. For a disorder medium, the randomness causes my index to saturate to order 1. If I have a crystal in the quantum optics limit, I have a purely real index that grows indefinitely. And so if you believe this kind of blue curve, and you believe that what we see in real life solids is empirically correct, the only natural hypothesis that you can make is that it's quantum chemistry itself that's killing the refractive index of a crystal and bringing it back to order 1. So what exactly do I mean when I say quantum chemistry or solid-state physics? Well, in principle, it's everything you can imagine. Okay, so if I could do an exact theory of quantum chemistry, it would include hybridization of orbitals, the fermionic statistics of electrons, Coulomb interactions, electron spin, etc. So just to say that kind of everything happens, and that's why your index is 1, that's not a very deep or enlightening statement. At a broad level, maybe it's not so surprising that chemistry makes the answer worse, because when chemistry turns on, it's kind of inevitable that new degrees of freedom become available to you. And then now when you shine in light, maybe light can somehow leak into those other degrees of freedom and kill the single mode response. So then what we want to do is simply try to quantify and elucidate that physics while including non-perturbative multiple scattering throughout the calculation. So to actually do that, we have to be a little bit more modest, right? Because if we say, I'm going to take on a real material, that's actually a very complicated problem, right? So we know that in computational chemistry, people invented all these kind of approximate techniques like density functional theory, et cetera. But these are very complicated problems, and we don't actually know exactly, or we can't fully justify, for example, density functional theory in the first place. Okay, so taking on a real material from really first principles seems to be too hard. So we're going to limit ourselves actually to this regime here, where the nuclei are still very far apart, and quantum chemistry is just starting to turn on. And then the kind of final picture, just to kind of preview the result, what we're looking for is that when quantum chemistry turns on, this previous picture that I introduced of single mode response gets modified, because the chemistry interactions, whatever they are, they might shift the resonance frequency of this collective mode somehow through the real part of some so-called self-energy. And then you would have an imaginary part of that self-energy, which simply says that when you shine in light, chemistry finds a way for that excitation to disappear rather than being radiatively emitted back into the same mode of light that I sent in. Okay? So let me just kind of explain a little bit more what the minimal model is, because again, the full problem must be very complicated. So first of all, just formally, when I say quantum chemistry, I mean the following. So here's my Hamiltonian. I have a set of electrons, 10 to the 23rd. They each have kinetic energy. They have a Coulomb attraction with nuclei. I have electron-electron repulsive interactions. And I have the interactions between the electrons and the photons. Okay, so that many-body problem is probably impossible to solve. To try and make it a little bit simpler, we're going to take the controlled chemistry limit, where the distance between nuclei is much bigger than the Bohr radius. Okay, so my electron orbitals are exponentially localized, and they're just starting to touch each other. So the minimal model you need is the following. So to talk about refractive index or optical response, I need at least two electronic orbital states, a ground state, which I'll call, let's say, 1s for hydrogen, an excited state, which could be 2p. It turns out for chemistry, you also have to start talking about the electron spin. Okay, so remember that up to now, when we have isolated atoms, the photon that you shine in doesn't couple to electron spin, it only couples to electronic orbitals. But once chemistry turns on, you actually do have to talk about spin. So I can have a 1s ground state, but I have to say that it's either spin up electron or spin down. So what can possibly happen once orbitals, once the nuclei start to get a little bit close to each other, is that an electron on one nucleus can start to tunnel over to an electron on a neighboring nucleus. And of course, you expect that that tunneling rate is exponentially weak in the distance of separation. You can also expect that if one electron manages to tunnel over to the next atom, that has a very large interaction energy. So an extra electron sitting on a nucleus gives rise to a large Coulomb interaction or a large on-site penalty, interaction energy penalty for that state to exist. So this kind of cartoon picture, if you're familiar with it, is just basically the minimal ingredients that you would put, that you would have for a so-called Fermi-Hubbard model. And then what makes it different from just the usual Fermi-Hubbard model is that we, at the same time, have these kind of photon-mediated interactions, or this kind of quantum spin model describing multiple scattering of light. So you can take this kind of minimal model and view it two ways. You might say that it's maybe some kind of hypothesized universality class of refractive index. So maybe it applies to a general class of atoms. Or you can say, well, if I have literally one electron per nucleus, this could be a quantitative model of hydrogen. Okay, so solid hydrogen is not a particularly realistic optical material, but you can nonetheless kind of take that as a simple toy model. So now let me just kind of, what I'm going into here, I don't expect you to kind of understand or remember all the details. The goal is really more to give you a flavor of the potential richness contained in this multiple scattering problem and the complexity that comes when you have strongly correlated physics. Okay? So the first thing that can happen when quantum chemistry turns on is the onset of quantum magnetism. So in particular, imagine we have two electrons. So the first problem we'll ask is, before you even shine in light, what's the true many-body ground state of this hydrogen lattice? So if I have two electrons sitting on two neighboring nuclei, I can have this process where one electron tunnels over to its neighbor. But because this on-site interaction is so big, that creates a very high energy state. So I shouldn't expect that that state exists in a real sense. But what I can do is I can kind of treat that as a kind of intermediate state within perturbation theory. So I can go back to a low energy state by having one of those electrons tunnel back. Okay, so this is just the visual picture of usual second order perturbation theory. And the point is that this intermediate state can only exist if these two electrons were pointing in opposite directions in terms of their spins, right, because of Pauli exclusion. So the fact that this intermediate state depends on the two spins pointing in opposite directions, within perturbation theory, that gives rise to an effective electron spin-spin interaction. So in particular, a kind of anti-ferromagnetic Heisenberg model. So of course, that kind of interaction strength of the spins is exponentially small in the distance between nuclei. So then the conclusion of this is that the true ground state of this hydrogen lattice would be one electron per nucleus, but where the spins are kind of alternating in a checkerboard pattern. So I have nail order. So the fact that I have kind of this checkerboard pattern in electron spins, that in itself does not affect the refractive index. Because again, remember that when I shine in light, the light doesn't care about the electron spin. But then if you go to, we can go to kind of the next order of perturbation theory. So again, in lowest order, I say that my ground state is exactly 1 electron per nucleus. But then within standard perturbation theory, at next order of perturbation theory, I should say that my true ground state has a little bit of this intermediate state mixed in. So my true ground state, if I were to take a cartoonish picture, is most of the time having 1 electron per site with this kind of checkerboard spin pattern. But once in a while, I really do see 2 electrons sitting on the same nucleus, and I see 1 nucleus that's empty. Okay? So this visual picture here basically means that you start to get density fluctuations in the electron density. And the point is that this state here is sensitive to light. Because as long as I have perfect order, then when I shine in light, that looks like my perfect mirror, my perfect single mode response. But now, in a manner a little bit kind of analogous to when we were talking about Rydberg interactions, when I have 2 electrons on a site and an empty site, that can't possibly respond to light in the same way. So I shine in light, these density fluctuations effectively look like little holes poked into my atomic mirror. And now this correlated ground state can scatter light into other directions randomly. Okay, so that's one mechanism by which you break single mode response. A second mechanism by which you break single mode response is the following. So imagine I shine in a photon. I excite 1 atom or 1 electron from the s orbital to a p orbital. And in a likewise fashion, this p orbital can start to tunnel over to the nearest neighbor. So that creates an intermediate state with a very high energy penalty. But then in perturbation theory, I can go back to a low energy state by having 1 electron, let's say the s orbital, tunnel back. So if you compare the initial and final states, you see that the p orbital is moving around. Okay, so I excited, so this electron directly absorbed the photon, but this excited electron is now able to tunnel and exchange places with a ground state electron. And what you see, if you look at the picture carefully, is it's not just the orbital energy that's moving, but actually the spin degree of freedom is moving along with it. So the fact that this p orbital happens to spin up, when this electron hops, it carries its spin over at the same time. So I have ps up, down, and this is now sp down, up. And the point is that now when this excited electron starts to tunnel, it starts to break the nail order in the system. So imagine I had a perfect checkerboard pattern in the spins, but then this excited electron tunneled upward, and this s orbital tunneled down. Now I have 3 electrons in a row pointing spin up. I no longer have perfect magnetic order. And that costs spin interaction energy. So when this excited electron eventually emits a photon, I can tell I have no longer, again, this perfect checkerboard pattern. I have spin interaction energy left behind because I'm now in a spin excited state. And that means the emitted photon cannot possibly be the same color or same energy as the photon I sent in. Okay, so it's an inelastic process, which for all practical purposes is the same as absorption of a photon. So it's not a coherent optical response. So those are really the 2 processes by which you can send in a photon, and the photon energy can kind of leak into directions or degrees of freedom you don't want. If you look as a function of lattice constant, you see that, okay, for large lattice constants, this bad stuff is exponentially small, but because it's exponential, as you shrink the lattice constant, it grows exponentially. And at some point, it really kind of overtakes this ideal electromagnetic single mode response. And when that happens, so at a distance of around 10 to 20 Bohr radii, you see that the refractive index that you predict by pure quantum optics theory starts to no longer hold. Your refractive index no longer stops increasing indefinitely. It hits a maximum and starts to go down. And at the same time, if you look at the imaginary part of the refractive index, it starts to go from 0 to a non-zero value. So your real part of the refractive index shrinks, your optical absorption goes up, exactly like what you would expect or what you see in a real material. So again, this is a kind of very minimal model, but it kind of starts to provide insights into why the refractive index of a real material, of a real crystal is so small. It really seems to be coming from quantum chemistry itself. And maybe one of the kind of punchlines is that, according to this minimal model, it does seem like an ultra-high index material with an index around 30 with low losses does seem to be allowed by the laws of nature. So again, ultra-high index materials seems to be possible in principle. There's a big question of, aside from the theory, can you actually design and synthesize a high index material, and how would you do so? I think what this problem shows is that there's really a kind of large hole in our theories of optical properties of materials. So just to kind of recap, most of the time in these lectures, we're really sitting at the boundary of quantum optics. So in quantum optics, our standard theories are the Maxwell-Bloch equations. What I tried to convince you of is that once the atoms become dense enough, then you have non-perturbative multiple light scattering. That can be an incredible resource if you're interested in things like quantum memories and photon-photon gates. It also leads to a lot of new complexity of quantum optics in the many-body regime. And what I showed just now is that there was even kind of a third axis of quantum chemistry. So as you transition away from kind of real atoms or cesium atoms to a real solid, there seems to be really something kind of non-trivial at that intersection of points. Okay. So then you could also ask, here we studied only linear refractive index. You could study any other material property or optical property that people might care about, non-linearities, et cetera. And you can ask, is it possible to develop a bottom-up approach to understand those properties? So with that, I'm done. Again, I hopefully convinced you that this problem of multiple scattering of light really adds a new, I think, exciting and also non-trivial chapter to our quantum optics textbooks. I think you get from the sense of just today's lecture that this kind of probably the biggest frontier left over is this kind of many-body regime. I try to give you a couple examples to illustrate that many-body regime really should be surprising and consequential. But if I were to keep going with the lectures, actually what you find is that there's not many things I could add on this list. Okay, so there's simply an infinite number of things, probably even very basic things we still don't understand. Of course, I know that you guys work in many different fields, but if you ever want to take up this kind of many-body regime of quantum optics someday, I hope that my lectures excited you, and I would encourage you to take on that problem and someday come back and tell me what the answer is, because I certainly don't know. So with that, thanks for your attention and for your time.